everybody, and welcome back to another episode of Adventures in Machine Learning. This week on our panel, we have Ben Wilson.
Hello.
I'm Charles Max Wood from Top End Devs, and this week we have a special guest, and that's Pier Paolo Ippolito.
Hello. Hello, everyone.
Do you want to introduce yourself real quick? Let us know who you are and what you do, why you're famous.
So, yes, I'm Pier, and I'm currently working as a data scientist at the SAS Institute in the UK. And part-time, in my spare time, I also contribute towards data science in publication online, and some of my articles also get published on other online publications as PreWorkCamp or Kiddy Nuggets and so on.
Awesome. I remember working my tail off to become a senior developer. I read every book I could get my hands on. I went to any conference I could and watched the videos about the things that I thought I needed to learn. And eventually, I got that senior developer job. And then I realized that the rest of my career looked just like where I was now. I mean, where was the rush I got from learning? What was I supposed to do to keep growing? And then I found it. I got the chance to mentor some developers. I started a podcast and helped many more developers. I did screencasts and helped even more developers. I kind of became a dev hero. And now I want to help you become one too. And if you're looking forward to something more than doing the same thing at a different job 3 years from now, then join the Dev Heroes Accelerator. I'll walk you through the process of building and growing a following and finding people that you can uniquely help as you build the next stage of your career. You can learn more at devheroesaccelerator.com. So you're a data scientist. I'm sorry, where did you say you were working? I didn't quite catch that.
The SAS Institute, SAS also software. So,
okay.
Yeah.
Very cool.
Your company headquarters is about 6 miles from my house.
Yes, in Cary.
Yes.
Yeah. Awesome. Well, you wrote an article talking about the paradoxes of data science. And in particular, you outlined 4 different paradoxes or 4 different things that you can run into with your data set. And as Ben is often fond of pointing out, your data kind of determines how good your machine learning models are. And so I thought, this would be interesting to dive into and talk about, how can we get a misread on our data? And how does that happen? So do you want to first, before we dive into these, give us a little bit of background on why you wrote this article, or, was there something that prompted this?
Yes. So I think the idea originally came from the research study I did for my master degree. So I did a master in artificial intelligence at the University of Southampton. And for my master, I decided to cover a topic called causal reasoning in machine learning. And part of the topic that I covered during the project that lasted about 3-4 months was researching about how causality can be embedded in machine learning models and what kind of problems you can have between getting wrong the relationship between causality and correlations in datasets, variables, and for example, how can this be applied also in the case of COVID or things like that. When you, for example, like as you might remember at the beginning of 2020, like February, January 2020, there were lots of people trying to, for example, think, let's see how AI can help with the pandemic development and try to stop or predict the number of cases and these kind of things. But at the beginning, and now they can do it also pretty well, but at the beginning was quite impossible because they didn't have any actual data to use to train their model or to create model in the first place. And that was sort of a paradox. And therefore, in order to try to solve this problem, you then have to work around other different techniques in order to augment the data or creating models, virtual environment as a synthetic environment in which are people moving around and spreading the virus, or using mathematical models to see how people can change states and so on. And that's what prompted then the writing of the article and so on. I think also the book by Julia Perla, The Book of Why, was also a really good starting point where he also explained the Simpson paradox, which is one of the 4 paradoxes I taught in the article.
Very cool. So do you find then, and I'm just curious as we get into this, do you find then that people tend to, they get more or better data? Are they able to overcome some of these issues with understanding the data? Or is this something that you fall into even with a good data set or a more mature data set?
Obviously, yes. If you have some process of data quality in the first place, that makes the work of the data scientist or decision maker itself easier. But you can still go into this kind of pitfalls. So you need to have some form of basics of knowing how the underlying system you're trying to model really works, and then you can model it so that you can make predictions on it.
Makes sense.
It's a very interesting set of topics that you brought up with simulation modeling when you have a sparsity of data coming into a problem. And this is something that as data scientists, we deal with quite a bit, where you might have a new project that your boss is saying, or somebody at the company says, here's a new initiative we need to solve for. Go figure it out, data scientists. And even if it's a very well-defined problem, which most of the time it's not, but sometimes it is, you go back to look in your data warehouse or in your data lake, and you suddenly have that sinking feeling of like, we don't even have this data. Talk to the front-end devs or back-end devs, you're like, hey, we're trying to look at this signal here. And they're like, oh yeah, we were going to capture that or put that in the logs, but we figured nobody would ever use it. So they turn it on, and you might have a month worth of work where you're trying to get everything started, doing your research, and then you just have a month worth of data to play with. And to make an effective algorithm, you actually need years of data, maybe to solve this problem. So what are some of the techniques that you found for doing that simulation of saying, like you said, people have been doing it with COVID, and how do they do that? Or how have you seen that done?
Sure. So yes, with regards to COVID, like you mentioned, I know there are two main approaches you can take. So one is with sort of epidemiology models, which are based on using differential equations. So in this case, for example, you could start by creating a set of ordinary differential equations, and each equation represents a compartment into the model. And then as you simulate and run these equations against time, then you can see how the different people in the number of people in your populations they move between a compartment to another into the simulation. And in this case, for example, the most simple model that you can think of could be an SIR model, which is a model with three compartments: people that are susceptible to a disease, people who are infected from a disease, and people who are recovered from a disease. And therefore, you have these three different compartments with these three equations representing the different compartments. And depending on the number of people that are in a compartment and the probability of moving within one compartment to another, you can then run a simulation. So which you can get the sort of curves that you might have seen quite a lot around with the peak of the pandemic and so on, that have been around used, for example, by different governments. For example, I know that at the early stage of the pandemic, the UK government was using the team from the Imperial College of London was using a sort of a compartmental model with something like 24 variables in order to spin 1 or 3. So that shows you also how complex this thing can go in order to make it more actually resemble the actual real world environment. Since that you can take into account as many variables as you want. So instead of having just susceptible, infected, recovered, enough a compartment for people who actually died because of the disease, a compartment of people who have been vaccinated and therefore they're immune from the disease, a compartment of people who have time-limited immunity. If they got COVID, they are immune for just a certain lapse of time and then they can get it again, and so on. So you can have as many compartments as you want in order to try to make it look as close as possible as the real world. And the other approach instead you can take is by using agent-based modeling. And this is used not just in epidemiology, but also like for example, for training military applications or for also vehicle simulations, like, for example, like they use in the Formula One car racing in order to simulate tracks and so on, and how a car can perform in a track. And in this case, yes, basically the main approach, one of the most standard one could be like to create a class, so an object-oriented class, and which represents, for example, a person in the population, and that's all the different characteristics which a person can have, such as an age or a certain type of commute that he might do within a city, and other factors such as being older, younger, female or male, and so on, so that to make sure that for each of these factors then it's associated a certain probability of getting the disease more, suffering more from a disease or not, and so on. And then you can instantiate as many people as possible using the class, and obviously run an algorithm to simulate how they interact with each other within an artificial environment, so that you can get exactly the same curves that you can get from epidemiology model-based.
So this is rooted in game theory and Bayesian probability statistics, where you're saying, hey, for a given population, I have N number of, say, if we're talking about COVID, we start with a loci of, say, 10 infected individuals, and we say, map out how many people you're going to come in contact with, and then what is that multiplicative effect or that geometric increase in the number of people that might be infected if people don't change their behavior based on the current state of reality. And you can kind of approach a bunch of different problems with doing this as well. I've personally worked with companies that have done this sort of approach with tracking like cell phone location data of customers, where they're saying, hey, we know where these people are in general. We don't know who they are. We just know a cell phone had an IP address ping that was triangulated to this street corner in Manhattan. And we know where they're kind of going, and we can simulate where they're going to go and where similar people to them are going to go next week or next month, and then sell that data effectively. So it's interesting to hear about these approaches for something that's really important, like a pandemic. What would you say is an effective strategy if somebody's thinking about applying these principles to their business from a data scientist perspective? This isn't traditional supervised learning. This isn't traditional deep learning, where everybody seems to be focusing on those two things in the data science world. How would you recommend people get started in this sphere of data science work?
Yeah, I think that's much more a niche type of application, since that for many cases you can sort of gather data easily, but for other cases, such as for example the beginning of the pandemic, you actually don't have anything. And that could be also for other applications, such as, for example, predicting escaping routes for volcano eruptions or things like that. When you want to model how many people can escape from a city if a volcano erupts. That's because you don't have much data about anything, or freeze an earthquake or things like that. You can just use this kind of modeling simulations. And that's where they become useful. But when you have data, obviously, it's better to try to use the real world data to fabricating some form of artificial data, which then you use to make the models. And in order to do that also, if anyone here listening is interested, in my case, for my project, I mainly created everything from scratch, since that was a custom application, let's say like that. But there are also some open source packages or libraries, such as Mesa, which is in Python, or Ash, which has also JavaScript in C++ API, which you can use. And they also provide you with some form of, for some common problems. Like could be, for example, some example they had was modeling the logistics. So optimizing the logistics for a store, for example, or modeling how a wildfire spreads in a forest. And for these kind of simulations, they also provide you out-of-the-box visualizations that you can use, so that you can actually focus just on creating the best model, instead of having also to create a fancy 2D or 3D graph, you showcase how the actual model evolves over time.
Yeah, there's a customer of my company's that has been working on tracking the population density of both predators and prey in a national park. And it was interesting talking to them and asking them a couple of questions like, hey, how do you do this and stuff? And they walk through it, and it's almost identical to what you're saying. It's like agent-based modeling. We're creating a set of conditions based on mathematical models. And they're basically just passing partial functions around inside this class saying, hey, here's the probability that this happens based on what we know of the interaction between these species on a very limited observer basis. But they want to forecast, like, what should we recommend to the federal government of the number of prey that humans can hunt versus how many are available for the predators, and how do we get an ecosystem balance? And it's one of those things that you can't actually run those tests in the real world because it has a huge impact. And you can't just run experiments, do like a design of experiments, but like, well, this year we're going to allow hunters to cull 40% of these creatures. You destroy an ecosystem doing that. So the way that they get around that is the simulation of saying, let's just run 1 million simulations and see what happens.
Yeah, that's also a quite common other application because I don't remember now the name, but there are a set of 2-3 equations which represent this kind of situation that are commonly used in this kind of application, like ordinary differential equations.
Yeah, it's really, really interesting for anybody who's listening who is really curious about some of these mathematical models. Some of these equations are very old that predict where stability will be for a particular population or a particular like natural phenomena, but it applies to a lot of other things as well. Trying to remember that one magical equation that gets a periodicity repeating But there's an equation out there that if you feed in a certain value into it, and I think it's in the denominator, it'll, based on what that value is, what that K value is, it will generate either a repeating binomial series or multinomial series that actually maps to observed data in populations. And it also translates to stuff like routing of vehicles, like how many paths can we actually successfully do in a steady state situation. So it's pretty fascinating stuff. So what are some of the other applications that you've seen for handling early stage serious problems that we need to solve now, such as the beginning of a pandemic and saying, what should we be focusing on, or how important is this?
Yeah, I think these are the most common ones. So then, for another thing I commonly see out there, for example, could be that for some cases where you don't have any data to start with, but you know that you can get data faster. You can also, in order to try to tune these models, you can also start with the modeling simulations, and then, for example, in the case of COVID, after 6 months, when you actually get the data, then compare the curves that were predicted with the actual ones, so that you can fine tune the models like hyperparameters almost, and then get better results. So that's definitely another one. And then, for example, apart from that, I see now there is also focus also for supervised models or unsupervised models to create actual synthetic data, for example, for actual machine learning problems, which could be like oversampling techniques, undersampling, or people, for example, I saw also different type of some big names in financial institutions creating synthetic data or financial analysis data and actually selling them as a product. So I think there is interest in this topic. Also, especially considering that data can be also quite expensive to buy, and creating your own synthetic data can be also an edge basically on other people.
Yes, so synthetic data creation, when we're talking about supervised learning, it can be a technique to sort of reduce the probability that your model is going to receive completely unexpected data and not know how to handle it. And we're talking about linear models. Your space is effectively contained by what your training set feature vector is. And if you get something that is such an outlier on enough of those vector positions, if they are dominant in that linear equation, you're going to get a prediction that is not going to make much sense. So, and tree-based approaches are even worse, where you're confined exactly to that sort of label space as well as the feature space. Outside of that, it's not going to extrapolate what could potentially happen. So simulations can sort of curtail the possibility that you're going to not respond to a black swan event, such as a pandemic crippling the financial industry of many companies. Are there any downsides that you've seen for people that are using your company software? Which is, I've only ever seen really SaaS users do this, because it's pretty sophisticated stuff to intelligently create synthetic data. But are there any downsides that you have of like warnings, like, hey, don't do this for this use case, or yeah, definitely do this?
I think it's quite user specific. So you always have to pay attention closely to what they're doing for. For example, an analytics center that we offer with SaaS is we use grants to create actual synthetic data. And I don't know how precisely that works, but it's something that they have been working the last few months for R&D for that. And but it's also quite important, for example, to remember in this case, like a quote from George Box, which he said that all models are essentially wrong, but some of them are useful. So there is always, because you are trying to make a prediction on a population from a sample, there is always going to be uncertainty and errors. So just keep in mind that. Keep that in mind and be sure that you always check for drift in the data or anything after you deploy the model, because the model is not an actual representation environment, but just an approximation of it.
And for most use cases, when we're talking about even something like modeling out pandemics, there's a lot of latent factors that go into that. I'd say the latent variables that are actually incredibly important for modeling that out are uncollectible data, unless we have, some sort of weird surveillance state going on in countries around the world where everybody has a camera on them at all times. We know exactly what you're doing, who you're talking to, with the proximity to physical interaction is. But for a lot of use cases that people are doing in industry, it's similar. You are trying to predict whether a customer is going to churn. You're trying to predict whether this activity is fraud. You're trying to figure out if somebody's going to buy this thing. The actual underlying influences, those latent factors that really drive what somebody is going to do, or that what the classification of that action is, are unknowable. It's not going to be in your training data. So how do you handle that? If you're talking to a lay person at a company and as a data scientist, and they're like, well, why doesn't the model get this right? How do you communicate that to them?
Yes, like obviously you need to make sure that when you ask us, you start by asking a business question. Once you set up your business question and you know what you're trying to achieve, you need to make sure that you have all the elements made that possible, because if you don't have the data necessary or the variables basically necessary in order to achieve that, then the only other way you can try to go for working out a solution could be sort of to find a proxy variable or something like that can communicate with the original variable that you are trying to interpret, but you don't have, but is connected with, so that you can sort of correlate between the two. That's I think the main way you could try to focus on that. And for example, one way to do that is by using Kalman filters and particle filters. That's something that can be used, especially if you see like in robotics or reinforcement learning type of applications, where you are trying to, for example, one actual good example is like if you're trying to track the position of a car where it's moving around the map or in the world, and there is going to be points in which, for example, the car might go under a tunnel or might go in a really weird post in like a forest or something, and there is street signal. And in order to try, for example, when you go under the tunnel to predict where is the car, you just take measurements of before and after you had information and try to work out what's going on in the middle, basically. And that's how this kind of particle filters or carbon filters can work, in order to estimate things with a proxy variable that you don't have. But that's just a very specific application. So, like, if you're working out with standard supervised learning techniques, then like feature engineering with the features you currently have and trying to see if you can work out how can they relate more to your business case is probably the best solution.
So feature interactions in particular of extrapolating the covariance associated with two separate features to provide further information. Is there a limit to that of how many elements or how many features in a vector that you would say, hey, don't go crazy. Don't do something like, hey, I'm going to throw 1,000 features into this model and I'm going to interact them all. What sort of output would you expect from something like that in supervised learning?
No, I mean, the general advice, I think, would always be to try to solve a really complicated problem in the most simple way possible. So, because especially even if you achieve really good results at the end and you have thousands of features, then and you actually want to deploy it, you always have to maintain it and make sure that you can sort of understand how the model works. And especially in some countries, like for example in the EU, there is the GDPR Act. There is an article for the right of explanation of a customer. So, for example, that could be if you create this model for deciding if someone should get a loan or not, and a person from doesn't get a loan, go to the bank and ask, okay, I didn't get a loan, I get it back. Can you explain why or what can I do to get it? And then the guy will say, okay, there is this model of 2,000 variables that does decide things for us. And I don't think that's a really good explanation.
Yeah, 100% agree. Even if somebody has 10,000 variables, it should be going through feature reduction and saying, I'm going to do exploratory data analysis. I'm going to interact features. I'm going to iteratively go through and do covariance estimates and cross-validation of different feature subsets and saying which ones actually solve the problem to keep it as the simplest artifact possible. That's something that I don't see nascent teams doing very often, unfortunately. And that's something that people assume, well, I can throw 10,000 features into XGBoost, and then I can calculate feature importances, and then I can just take the top N, and then you have to kind of explain to them, like, that's not how you do it. You need to use other tools, statistical tools to determine.
It sounds so smart, though.
It sounds lazy. And as engineers, a lot of us are lazy, right? We want to get to the next thing pretty quickly, and it seems like it's a good idea or that it can save you a lot of time. It actually just wastes a ton of time from every time I've seen somebody try to do that. You run into another interesting problem with supervised learning where the curse of dimensionality, as that feature space grows, you now need more rows of training data for a model to even detect a correlation signal correctly. And that becomes, exactly as you said, Pierre, it becomes expensive to start having to have that volume of training data and gets complicated.
I did think it's even more interesting now with how the whole field of transformers are evolving with semi-supervised learning. And for example, how they started with NLP and now they are going out to also vision data or sound data. So I think that's also going to be interesting next year, how that is going to go on.
Into sound data. So can you talk a little bit more about that, about what that research is like?
No, but I just said because I know that Hugging Face recently launched a new feature on that. So they are basically, you can use also like transform, you can transcribe NLP data and then process it or anything like that. And I know, for example, also Unity, the gaming engine, is doing quite a bit of research on that, and also on synthetic data, since that obviously you have this sort of modeling environments like we mentioned before, like data used for games, so they're trying to take advantage of them also for AI now.
Hey folks, it's Charles Max Wood, and I just wanted to jump in here and let you know about something that I'm doing. It's free. It's out there just to help you get answers to your questions about the things that you're running into with your career. So if you have questions about how to get further ahead in your career, how to start a podcast, how to get a better job, how to get a raise, how to deal with a situation at work with your boss, or just maybe you're stuck and you don't know where to go next. How do I get from junior to senior to whatever's next? How do I become a speaker? How do I get to the next level? That's what I'm out here to do. So every Wednesday at 12 o'clock Mountain Time, I'm going to be doing a call, and it's going to be free, totally free. Go to devchat.tv/levelup, and you can register for the call. It's using Zoom's webinar software, so it's pretty straightforward. And what we're going to be doing is I'll do 10 minutes, and I'll just show you how I do some form of how I level up, and then we'll just answer questions. And it's not going to be a question and answer like, hey, what's your favorite flavor of ice cream? And then I say Rocky Road or whatever, right? Instead, what we're looking for is more along the lines of, I have this situation. How do I handle it? I'm trying to figure this thing out. How do I figure it out? I'm trying to stay current. How do I stay current? And if you have any of those kinds of questions, I'll bring you on the call. We'll ask some deeper questions. We'll make sure we get you a solid answer. And I'm really looking forward to helping some people out. There will be no sales, no selling, no nothing on these calls. It is literally just 10 minutes of training and then Q&A. So you can go check it out at devchat.tv/levelup.
Interesting. So because you have hardware that's running that game engine that has generally free cycles of a pretty beefy GPU sitting in a desktop, if people are running that, you can just have a portion of those threads in CUDA running a simulation at any given time so that you get dynamic gaming effects that respond to player input and how they're playing the game.
Yeah, I also know that Unity can be used with Python in order to create actual RL models. So they are exploring on that. I don't know how precisely they're going to use it internally, since I never worked for them or I don't know anyone working for them. But for sure, they have interesting stuff. Since they developed SDK and everything, they are quite interesting in that area.
That'd be an interesting metamorphosis of video games in general. Or if you can have what's that?
No, it's like also Unreal Engine with optimizing, for example, ray tracing or things like that. They use also AI for these kind of things, and that's also in gaming. So that's and you can see how, for example, you can bring ray tracing to machines that before couldn't be able to handle it. And so there is definitely quite a lot of room of improvement for this kind of applications.
Yeah, currently ray tracing on GPUs, that's a brute force algorithm. It's going through and calculating every point of a light source to every surface that it's rendering. If you can have an AI solve those where that
solution and make it much faster.
Yeah. So it doesn't have to do that pathing calculation. That's pretty interesting. It's almost like using an autoencoder to say, here's what my expectation should be from this point source in this location. Now just render the frame for me on the next cycle. That's pretty cool.
So one thing that, kind of pulling it back toward this article a little bit, do you find that these paradoxes, because you gave visualizations, and so for me, I looked at them and I was thinking, well, I can see how I could come to that conclusion based on what I'm seeing on this graph. But do you find that these paradoxes affect the accuracy of machine learning models? Or is it just something that we fall into as we look at the data and kind of try and find a pattern ourselves?
I think if you don't give the models all the variables that it needs to actually solve the paradox, then it also can get trapped in it. Like in this case, for example, we were neglecting, in the case of the example on the article, I think we were neglecting the age as a variable, and the paradox. And then if you just give the levels and the exercise and you neglect the age, then the model could get confused, since that it just looks at how the different features compare to each other, correlate to each other, and make prediction based on that. It doesn't have any external knowledge like we human can actually do.
Oh, got a bunch of dead space. That'll be edited out. Sorry, I was just looking over your the article real quick because I couldn't find the exact link to that one. But Simpson's paradox, that's one of my favorite ones to explain.
Yeah, again, right, it gets back to, because, I looked at it and I kind of did the lazy evaluation and was going, it looks like it says this, instead of actually applying a little bit of rigor and going, oh, this is what these numbers actually tell me.
Yeah, so one of the things that I really like about that article is not just the explanation, which is great. And I find that I am fascinated by your reading style because I read a bunch of other things that you had posted over the past couple of days. But the plots, the visualizations that you use to actually tell that story are something that I don't see a lot of people doing. I see not a lot of newer data scientists, I'll call, people that have gotten into this field in the last 5, 6 years. I see these explanations coming, or I used to see them all the time back when we used to be called analysis engineers or statisticians. But this used to be the bread and butter of everybody's analysis. Before you even talk about modeling, you have to go through, and in this article, you're in the Simpson's paradox explanation, you're going through and creating this visualization where you're displaying the Pearson's correlation coefficient of these two variables and saying, this is how they're related. Here's my evidence of fitting a line to this and how correlated they are to one another, and extrapolating from that, what is the interaction between these features? How closely related are they? How critical do you think it is for pretty much any ML to go through this exercise that you did in explaining and teaching this on just general features? And when do you think that's an appropriate time to do it in an ML project?
Yeah, I particularly like for creating good data researches. That's one of my favorite things when I'm creating a model, creating an analysis basically. So, and that's also why, for example, some of my favorite articles and some also that the one I got more well received were also articles in which I really took time also to create interactive visualizations. So like, for example, some of them that I also embedded, 3D plots you can actually rotate or play. For example, for explaining how hyperparameters works and how to find the best combination of hyperparameters. Or working with autoencoders, creating deploying, for example, an encoder using on an X and actually be able to draw on it on a web interface. That's the type of experience you can actually test the model and see how it relates to the output and then work out what's going on. Because you make it more interactive and easier to understand, especially because as I mentioned before, I think the objective should always be to try to create the simplest solution to a complex problem. And in order to do that, you need to dive deep into what you're trying to model, first of all. And using visualization is one of the easiest way to do that, because otherwise you can also, create summary statistics and things like that can help you, but without actually seeing how the things works out on a graph. And I think that's just give you a part of the view that you might be missing out, especially as I said before, also reducing the dimensionality of your data and using PCA autoencoders or anything like that. also really helps, especially when you work with really sparse data or with text data that you have to convert into numeric format. And I think that's also a good example, like of, for example, So I think that data preparation, so engineering your features and actually be able to extract them, so that also you as a user creating the model, you can understand how you would predict based on this data. That really helps working out things easier. And that also really, for example, like how I would really rate this to for example, how the Pareto principle works, like how doing a few things really well to give you 80% of the outcome or something like that.
Yeah, totally. And creating those charts and plots from my own personal experience, I don't know if I'm just old school, but I look at the charts that you created for these articles, your correlation plots. I'm like, man, I do that too. So like, I do it in that way, and I'll color code based on, label cuts that I do on the data. And, I'm looking at continuous series, but I'll save them all off somewhere so that after I've gone through, testing a bunch of different model approaches, trying to find the simplest, most performance, cheapest solution generally, I always go back and look at those when I'm trying to do interpretability analysis, where I'm running, say, SHAP on top of that model and saying, hey, figure out, I'm going to sample 1,000 rows from the data set, and I want to see the force plots for SHAP for these. But when I'm looking at those, I have the correlation plots open right next to me with all of the color coding, and I'll look and I'll say, oh yeah, that makes sense why the model has learned that, because the correlation relationship between these is this. And even creating synthetic rows to run it through SHAP testing and then referencing these correlation plots, that can help figure out where that space is. And yeah, it's super critical, I think. And hopefully more people can read and look at the examples that you've done in these articles, because it's an insight into how it's supposed to be done when you're going through a deep analysis of your data.
Thank you.
Yeah, that Simpson's paradox, that's probably my favorite one. That can be the most interesting paradoxical discussion that you can have on a data set, because it exists pretty consistently, I've found, in real world data, where if you just plot a continuous variable against another continuous variable, or if you're doing, an ANOVA analysis of categorical data and you're visualizing that, it can be pretty misleading because there's some confounding variable that is actually explaining that noise that exists in that plot. And if you don't actually color code that or map that or split that and do that per sampled subgroup analysis, you might lose that signal in explainability. You use the age versus cholesterol level in your example, but it's pretty rare that I've found an actual real world use case where I don't see interactions like that happening. So to the listeners out there, I highly recommend reading that article in particular from him, because it really does break down some of the ways that you can get burned in ML without really understanding your feature data. Oh, we had another pause.
Yeah. I'm just wondering, what other gotchas can you run into? And is there a good way to make sure that you're not running up against that stuff?
I think the accuracy paradox is, for example, I compare it to the overfitting. So how trying to, for example, focus too much on small things can then stray away from the bigger picture and make you lose points when trying to actually predict on real world data. Mm-hmm. So, and that is also another thing which is quite common, because at times, especially you might try to use, when you try to use more models more complicated than necessary, then that's usually what happens. Like you overfit to the actual training data, and then when you try to make predictions on out of sample data points, you get worse performances. So, and basically that's also why it's a paradox, because when you try to create a model, when we actually train it, you try to improve the accuracy as much as possible. But when you test it then after on the test set or validation set, you just notice that trying to improve the accuracy in the first place then led to worse accuracy when you actually need it later on and in production. And that's why it's really important to not focus too much on if you make of your own target the only thing that matters, then it stops being a good target. Like because that strays your way to the actual process, which you've been in between creating a new product.
Yeah, I mean, I'd say that it's endemic, and I have a name for it that I use. I call it the Kaggle paradox, even though it is the accuracy paradox, but it's almost the fetishization that data scientists have these days of competing, of like sort of winning the accuracy game at the expense of maintainability and explainability. I've seen people spend months on projects that they could have solved something at an accuracy value for a classification. For instance, like a binary classifier, they could have had an area under ROC of 0.94, and they could have done that in a week's worth of work of building a very simple model, just doing their feature engineering to get it to be somewhat accurate. And on a holdout validation, they would have a result like that. Instead, they spend 7, 8, 9 months working with an ensemble of, an implementation of basically somebody's white paper that hasn't been proven or referenced. And they install PyTorch and they build this graph embedding solution that I think is going to, work really well. And after that almost year of work, their result on the same holdout validation is 0.957. It's like, was that really worth it? I mean, it's cool, I guess, to build something like that, but how expensive is that going to be to maintain? And can you explain that, like how it arrived at that prediction?
Also, in terms of carbon footprint, it's probably not the best. And I saw about it a few weeks ago, a tweet or something online, or maybe also LinkedIn, of someone saying like, yes, if you are a data scientist now and you have to solve a problem of a model you have to take in production, and you have to solve a problem, there are two things you need to do. First, create a linear model which can go into production, and then spend months creating a really weird and sophisticated model so that you can just put it on your CV later.
Yeah, I mean, resume-driven development is a thing. I've seen entire groups at companies just dedicate themselves to that. They just want to do the most cutting-edge thing, and it does a disservice to that company when you have an entire team with that mentality. When that baseline, that first attempt, I don't even use linear models to do my baseline, by the way. I'll do a simple fit of like a simple regressor. If I'm doing, a regression style problem, if I'm doing categorical, I'll just use an if-else statement based on an EDA. I kind of have a breakdown in my head of like, okay, here's the relationship. If the values are between this and this, it kind of correlates to this for a prediction, and write a very simple decision tree in SQL. But that's my baseline to compare everything else against while I'm doing experimentation. But I time box everything too. I'm like, hey, if I'm testing out an algorithm, it gets 48 hours of attention. That's it. If I can make it work and it seems promising in that 48 hours, it's a candidate. If it's too complex or the API just sucks so bad that it's almost unusable, it's out of contention because it's going to take too much time and money. And as you said, carbon footprint, that's a real thing. Electrons are precious. They come from fossil fuels generally, so don't waste them.
But I like electrons.
Everybody does.
Yep.
But the overfitting, underfitting stuff with that effect, and in the pursuit of accuracy at all costs, it also comes with it a process that you need to adhere to while you're developing stuff, where you see people doing stuff like hyperparameter tuning with grid search and cross-validation, where they're running through and they're doing random splits. Maybe they're stratified, maybe they're not. They're doing undersampling, oversampling if they have a massive class imbalance. And when you're doing that random iteration of cutting for train and test and over and stuff, what do you recommend for that final evaluation when you're talking to people about avoiding the accuracy trap of this situation where you're saying, hey, you're pursuing the ultimate, cross-validated accuracy measurement above all else? How do you make sure to say, hey, this, at least you have confidence in production that this is going to work pretty well?
In this case, probably, if it's a classification problem, make sure that there is a good balance between different classes, first of all. Then then use precision and sensitivity to guide you, not just accuracy. And then look at the ROC curves and also the lift or this kind of metrics in order to keep track of how they vary from training to validation to actual testing. And also probe your model with the testing. Also come up with some good auto-sample measurements or something like that you can actually test it on to see if the model can react weirdly from some specifically edge cases, like you will do when creating an actual piece of software that you think of edge cases that might trigger your model wrongly. And so that you can probe also, where are actually the decision boundaries that your model is using and where it can go wrong or not, or how to change the margins or these kind of things. And that can be also important, for example, for a security point of view, because in theory, when you talk about cybersecurity attacks with ML, there are actually spyware of people trying to probe these models to actually understand where they draw a line at the prediction and then go past them in this way. So that's actually something that's also sort of can be a penetration testing for ML, like making sure that you understand how your model can get triggered wrong, so that you can actually monitor it for production if someone is still using for that.
That's funny that you mentioned that. I think we talked about that a couple of weeks ago, Charles. One of the guests we were talking about fraud detection and how hackers actually, how criminal hackers actually try to detect what they can get away with of, running brute force simulation attacks. And that's what they're actually doing. They're building this sort of table of saying, I'm going to do these actions in this order, try that with a burner account, see what happens. Now I'm going to try another thing. Where do I actually not get detected for doing something illegal? And that's where they'll operate. Like, hey, your system doesn't detect this, and I'm gonna steal a couple $100,000 from you. You're not going to even know. And it actually does happen. And so you brought up a great point. It's something that a lot of financial institutions do with that simulation. They have white hat hackers effectively that are trying to defeat that algorithm and say, hey, this is definitely some suspicious behavior. Let's see how the model behaves with it. And if it doesn't detect it, then they know, okay, we got to retrain or continuously retrain and monitor for those edge cases.
Yeah, and that shows us also how creating overly complicated models like this will sort of a law of unintended consequences when you as a triggering input then cause a sequence of actions which you wouldn't have expected, and everything falls down.
Mm-hmm. Yeah, with some of the interactions that happen with super complex architectures, there's no way that a human can reason about how the internals of that work. And that's why my advice to people is always, if it's something that is so important that there's a lot of money on the line, or your team's existence is on the line as a data science team in a bigger company, it has to be something that you actually understand how it's reasoning through the correlations that you're providing it. Because if you can't, think about the worst case scenario where people rely on the output of this implementation to make a decision that influences, say, 10% of your company's revenue, which could be 50 times or 100 times your entire team's budget. Think about what an executive is going to think about if you cause that amount of damage to the company because of your model. So understanding how it works is far more important than, as you said, that resume candy, like, oh, we built this cool thing and I'm going to put it on our CV. It's like people respect the fact that you put out 10 linear models that actually worked and provided value far more than that super cool reinforcement learning system that was so overkill for predicting churn of a customer.
Yeah, but I want to prove how cool I am.
I mean, I tell people that's what the weekends are for. Nights and weekends, do some cool stuff. And that's actually what Kaggle's for. Like use that tool for what it is. It's your way of showing off and building a portfolio if you want to be that person. But when you're working for a company, you got to take it seriously. And you need to produce something that is maintainable, solves a problem, and is explainable.
Yeah. Cool.
That seems to be a common theme in almost all of your articles, is like talking about that foundation aspect of data science work. And I personally find it fascinating seeing somebody who comes from academia sort of rigor of how to do stuff. And you've converted it into something that I don't see a lot of people do, which is real world practical advice on here's how this should be done. But your posts aren't filled with pages and pages of mathematical proofs. They're more like, here's some charts and visualizations. Here's me explaining why this is a thing. And here's a link to the proofs and stuff. Or, you want to read about it, here's where you go read about it. But here's something that, everybody can consume. I think it's fascinating. I hope you write a book, man, because I like your style.
I might in the future.
Yeah, when you're a famous, world-renowned data scientist, remember us.
I don't know. I think that might never happen.
All right. Well, we're kind of getting toward the end of our time. I just want to, call out the article again because I thought it was really well done. Ben's pointed that out as well a couple of times. If people want to find more stuff from you or, maybe connect with you and ask you questions, usually we're looking at like LinkedIn or GitHub or Twitter or something like that. And then it looks like you're also on Medium. Do you want to just let people know where they can find you?
Sure. So they can message me, or anyone can message me on LinkedIn if they need to, or they can also go to my website where I have a contact page. If you want to send me an email, you can do it through there. And I also have a newsletter, so you can really subscribe also to the newsletter to get updated when a new article comes out.
Awesome.
Nice. Hey, folks, if you love this podcast and would like to support the show, or if you wish you could listen without the sponsorship messages, then you're in luck. We're setting up new premium podcast feeds where you can get all of the episodes released after Christmas 2020 without the ads. Signing up will help us pay for editing and production, and you can go sign up at devchat.tv/premium. All right. Well, let's go ahead and do some picks. Now, picks are just shout outs, stuff we like, stuff we want to let people know about. Ben, do you want to start us out?
Oh, I've got a nerd pick this week. And it's what's consumed a lot of my time this week, which is working on libraries in Python. And I hadn't used it before that much because a lot of the stuff that I'd been doing of the last several years were sort of applications engineering, like using somebody else's APIs, and now working on stuff that building from scratch for other people to use, getting into the Pydantic library and doing something that is runtime type checking for Python. That is a fantastic library. Massive kudos to the engineers that built that and open sourced it. It powers a lot of the stuff that's in Fast API, which is a also amazing package that's out there. But type checking is good. It helps you write far easier and more knowledgeable and readable unit tests, and catches a lot of errors that you might otherwise miss with a non-compiled language.
Yep. Very cool. I'm going to jump in with a few picks of my own. I think last week I picked the 360-degree leader, but I'm going to pick it again just because I've wound up doing a bunch of coaching and I answered some questions on our weekly Q&A call, which you can find at topenddevs.com. Just scroll down, it's under events. But anyway, people have been asking, how do I manage this, or how do I deal with this, or my boss is doing this. And this book really does kind of outline, hey, here's how you deal with people who are, above you. Here's how you deal with the people that are around you, and here's how you deal with the people that work under you. And it really is just a terrific book that outlines a lot of that and a lot of the approaches and how to be a leader, even if you don't have like lead dev or manager or CTO or something for a title. You can still lead on your team. And I think it's an important skill to have, to be able to just let people know, hey, look, you can make a difference wherever you're put. So I'm going to shout out about that. Also, Top End Devs. So as this goes out, because I think this will go out next week, it's either next week or the week after as we record this, Top End Devs is getting a new website. And I've really just gotten a lot of clarity on what I would like Top End Devs to be, and, what our mission is for the dev community and things like that. And so the couple of things that are going on there, one is that I am working with people to put together courses on various things related to software development, but I'm also tapping into, I have a lot of friends who work not necessarily in tech or dev, but are experts in some of the soft skills that I believe technical people need. And so we're probably going to have some master classes and or courses on things like networking, and not like IT networking, but like networking with people or speaking at conferences or some of the leadership stuff that I talked about with 360-degree leaders, or how to find a job, or how to collaborate with other people and pairing and stuff like that. And then I do intend to also have the technical content. So if you're interested in authoring any of these courses, go to topenddevs.com/author. We're looking at video content and some audio content on the premium end. The podcasts aren't going anywhere, but this is kind of the next stage of where I see things going for us and for ways that we can make a difference for all of you. So anyway, I'm going to pick that. And then if you are looking for sort of one-on-one walkthrough coaching, typically people are getting on because they want to talk to me about creating a media channel like a YouTube video or a podcast. So I've been coaching people on that. I've also been coaching people on going freelance, and I've been coaching people on just kind of taking the next stage of their career. So if you're interested in any of that, you can also go to topenddevs.com/coaching and see what's offered there. So I'm going to shout out about all that. And then I am going to do a board game pick. I need to start keeping track of what I'm picking so that I don't repeat. But last Saturday, I was teaching people how to play games at a video game convention here in Utah. It was a rather small one. And I did it as part of a marketing push for a friend of mine who owns a board game store here in Utah. And the game we played, we taught like 6 games, but the one that I learned on Saturday before I had to take my turn teaching was Planet X, Search for Planet X. So if you like logic puzzles and you kind of like the dynamic of trying to figure out what the answer is, like Clue, they kept comparing it to Clue, but this game is way more fun. Go check it out, the Search for Planet X. You do need at least one smartphone in order to play it, but essentially what it is it's just the piece of the game that gives you the clues, right? So it's, hey, here are the clues you're going to get, and then when you do research or you survey part of the night sky for items, right, it'll fill you in and say, okay, there's so many asteroids here or whatever. But it was way fun, and so I really I enjoyed it, and I'm going to pick it. So go check out the Search for Planet X. We'll have links to all that in the show notes. Pierre, what are your picks?
For me, probably the Book of Why, like I mentioned before, by GitHub, in case you're interested into digging more about causality or the sort of paradoxes and why it's important to make models explainable and that I can embed some form of external knowledge of the world. So yeah, that probably is my pick for in this case.
All right. Very cool. Well, thanks for coming. This was a lot of fun. I almost asked you where people could connect with you again. We'll make sure all that winds up in the show notes. But yeah, I just love thinking through some of this process and going, okay, how do I make sure that the foundational data for my models is correct and giving me the right information? And then from there, yeah, now how do I build this so that it's useful to people? So this was really helpful.
Mm-hmm. Yeah, it's great.
Sure. Thank you very much for inviting me today.
Yeah. All right, folks, we're going to wrap it up here. Until next time, max out.
Bye.
Thank you.
Bandwidth for this segment is provided by CacheFly, the world's fastest CDN. Deliver your content fast with CacheFly. Visit CacheFly.com to learn more.